What's it called? Thank you all for contributing to such an excellent summer school. Me and Jakob are here representing Group 8. We're so excited to talk to you about it, and it's all centered on deriving the dust properties of local galaxies from the Dustpedia sample. My name is Amy Ralston. I'm a PhD student coming to you live from the University of California, Irvine.
Hi, and I am Jakob den Brock. I'm a PhD student from the University of Bonn. And of course, we're also happy to talk in the name of the other participants who took part in this project.
So as a collaboration between 6 European institutions, Dustpedia is a project that has compiled extensive multi-wavelength data all the way from the UV to the microwave of 875 nearby extended galaxies. This usually results in around 25 bands of coverage per galaxy. These rich data sets were created for the express purpose of allowing us to study the major contributions of dust to the properties of the ISM and the process of star formation generally. So we did just this in our hands-on project by fitting the photometric data points for various galaxies to the spectral energy distributions. Shown here is an example SED of M51 with all the different telescopes. So in normal galaxies, a significant fraction of the energy emitted by stars, probably around 30%, is absorbed by dust and re-radiated into the far IR in the 3 micron to 1 millimeter spectral range, which the Herschel bands, seen here in red, advantageously target. Thus, in our project, by performing SED fitting with the program CIGALE, we were able to infer properties like the dust mass, the star formation rate surface densities, and the dust grain properties for every single pixel in the image. However, in order to do this with every single pixel rather than the net effects of the entire galaxy, we first had to homogenize the data set.
The first challenge was to go from a multi-wavelength heterogeneous data set to then a homogenized data set. So here, as an example for M51, we had 24 observations reaching from the far ultraviolet up to the infrared. And so already here you see the differences. For example, we have here higher resolution bands, lower resolution bands. We have foreground stars. We have here a coarser width. And so the goal to then really have SED per pixel, we need to then homogenize it. So that is here the goal you see here down below. After removing the background emission, masking foreground stars, convolving to the same resolution, so to the lowest resolution, and then regridding onto the same rectangular grid, allows us then to compute such an SED for every individual pixel. So here for the center of the galaxy, or then here for the center of the companion, we have different SEDs. And so if you're interested, this whole data preparation, we have provided a pipeline on GitHub, which then does exactly this from a set of observations. It gives you then a homogenized data set in a table form that can be read into CIGALE.
So as you've heard previously from other groups today, CIGALE is an SED fitting code, which is able to statistically derive the best fit physical properties of a galaxy. It's based upon the energy balance principle and utilizes really realistic dust models, which take into account the stochastic heating of small dust grains and PAHs. So when using CIGALE, the great thing is you only have to provide 2 things. The first is the input file with the fluxes in millijanskis for each filter you choose and redshift for each galaxy. An example file is shown here on the top of the slide, where you can list all the available filters with pCIGALE filters list. And all of this is contained in the .init file, along with all the possible values that you provide for the physical parameters, such as star formation history and your dust attenuation. Then, using different models, libraries, and templates, such as Themis, if you so choose a realistic dust model, CIGALE calculates all the possible spectra, as well as likely fluxes for the filter bands that you've chosen. And lastly, once all the different models have been computed, CIGALE utilizes Bayesian techniques in particular to select the best fit model and physical parameters for each galaxy, or in our case, each pixel.
So this is what the results looks like. And as a reminder, for every individual pixel, we have such an SED. And so CIGALE gives us really a best fit solution for every individual pixel. And so then we can infer the galactic properties and can map them to really study the spatial variation of these properties. For example, you see here the dust mass. And then we can really look at the spatial variation. For example, here we see that the invert dust mass in the center is higher as opposed to the galactic disk. Or here we look at the small grain mass fraction, and also here we see variation between different regions in the galaxy. I could, of course, go on with the many more plots we made of different galactic properties. However, in the interest of time, maybe another interesting aspect we investigated was the impact of the model resolution and model selection, with the impact it had on the inferred properties. So what do we mean by that? So with resolution, as said, with CIGALE, we first compute a set of models, and that we then compare to the observed SEDs. And so what you see here towards the left, so this is always the dust mass surface density, or using 90K, 400K, or 5 million models. And especially going from 400K to 5 million models, you see that here in regions where previously the SED failed completely, with the increase of model numbers, we now seem to better account for these SEDs with the models. So when using these models, of course, one also needs to be aware of the number of models and the impact it has on the inferred parameters. And another aspect we looked at were different dust models. So here on the right panel, what you see is a set of global SEDs for a sample of galaxies. And on the x-axis, you see the inferred dust surface mass density using the THEMIS dust model, and the y-axis using an updated Drain and Lee model. And here we see that systematically we seem to infer higher dust masses using this model over the THEMIS model. So if we select a certain dust model, we need to also be aware of the impact it has on the inferred parameters. So with that, I leave you with our summary slide. As that, if you're interested in the data processing pipeline, you can check it out on GitHub. And we are happy to answer any questions that you might have. Thank you.
Thank you. So there are a few questions. Is the masking of foreground star changing something in the SED, or is it negligible?
So there are two ways. So either we really masked out these pixels. So then I guess it wouldn't impact it because we do not look at these pixels. Otherwise, another way we could do is then use an interpolation. And then indeed, it could impact the SED. So this is, if I can go back, this is what you see here. So here you see the masked out region in this, and here you see that an interpolation was used, and here the fit does not seem to be well constrained. So here, indeed, it could be that this masking and then the interpolation does not produce a well constrained SED.
Thank you. And another question, there are more questions that you will need to answer later. So did you have to choose a fixed dust emissivity index for your fit, especially in the far infrared, or did you allow this property to vary?
So I think, so it depends how many models we used, but in the case where we used many models there, I think we allowed this also to vary.
Okay, thank you.